Thanks everyone for joining us. Very excited to have Franziska here with us today. Franziska is joining us currently from the Vector Institute. She has completed a master's degree in computer science at Freie University in Berlin and Technical University at Eindhoven. For the past 2.5 years, she's been working at Fraunhofer AISEC as a research associate in topics related to privacy-preserving machine learning, data protection, and intellectual property protection for neural networks. Currently, she's a visiting research intern at the Vector Institute in Toronto in Nicolas Papernot's lab in Trustworthy Machine Learning. And she's also pursuing her PhD in Berlin. Thank you so much for joining us, Franziska. Very excited to talk about this new paper that you've written with Nicolas and his lab.
Yeah, thank you, Patricia, for having me. I'm also very excited to talk about it with you here. And of course, I'm also grateful for any feedback that you or any of the participants might have.
Excellent, thank you. Everybody feel free to either post questions in the Q&A or in the chat as we discuss. I'll start off with, can you please explain what federated learning is and how it works?
Sure. So in very short, federated learning is just a framework for distributed machine learning. To go a bit more in detail, I'll explain the vanilla version of it. Of course, there are several flavors, but I think for the sake of here, it's enough to understand the general concepts. So basically in federated learning, we have two central roles. One is a central party, basically a server who orchestrates this distributed machine learning protocol. The server creates and initializes a shared machine learning model and then organizes the trainings among the clients. And the clients are often or usually mobile devices that hold their own and potentially sensitive data. And they participate in the training. Not in every round of the protocol, all of the clients participate, but instead in every round when the machine learning model is trained, a subset of clients, like several hundreds or several thousands, are selected, usually by the server. And then basically the real process starts. And the first step in the process is that the server sends out this shared model to all the clients. The clients then compute the local gradients, or more generally speaking, just updates for this model on their local data for the received model. And then once they've calculated these, the clients send their gradients back to the server. The server aggregates these clients and then applies them to the shared model. And afterwards, the whole process starts again. So there's a new round, a new client selection, sending out the model again, calculating the gradients at the users and aggregating them at the server, updating the model. And therefore, we can basically think federated learning as a form of decentralized mini-batch stochastic gradient descent, where basically every client calculates the gradients of their batch of data, and then the server does the aggregation of the different batches. And of course, as I said, there are different flavors of federated learning. For example, there can be variation in how the clients are selected, by whom they are selected. And therefore, federated learning is more like an umbrella term for all similar methods. But in general, like the plain vanilla version is just like I explained. And the question, of course, arises, why is federated learning used in the first place and what are the benefits? And in general, we know that machine learning models, they train much better if we have larger amounts of data or if we have we have more diverse data. And of course, this is what we can achieve through federated learning because we have data from many clients. So we have larger amounts of data. And since these clients are potentially all different, we also have more heterogeneous data and might thereby end up with better model. And another benefit is also that we have some continuity in the learning. So the models are constantly improved based on up-to-date data of the clients. And there's no need to aggregate over like timeframes again and to check whether the model is still valid. And the question is, of course, why do we not just collect the data from the clients and like we used to do and take them to the server and basically perform a centralized machine learning model? Where there are several reasons why we wouldn't do that. And the first one is that sending large amounts of volume of data creates a communication overhead. Furthermore, the server would have to store all this data. And then the server would also be in charge of processing the data according to prevalent privacy laws. And probably most importantly, sharing such sensitive data like we have on the user devices in the plain format with the server might, of course, represent a privacy threat for the users. And therefore, like the idea behind federated learning is that we can get rid of all of this by just keeping the data locally. and just sending the client updates. And therefore, for a long time, federated learning was also sold as a kind of privacy preserving technology, because the user data never leaves the devices. And at least it was thought to have thereby some form of confidentiality. However, already some prior research work had shown that this protection is just a thin facade, because the model gradients that are sent from the users to the server still leak some information on the user's training data. However, many of previous work that looked into reconstructing the data from the gradients, they were kind of limited because they required lots of computations. So for example, they relied on high order optimization or GANs, like generative adversarial networks, to reconstruct some data that would produce the gradients like the ones that were observed. And basically, through this computational complexity, these methods were usually not very adequate for high dimensional data, or for data from the same class, or for data over large mini batches, because all of that makes just this optimization more complicated. And therefore, most of them, in particular in these difficult cases that I just named, they just fail to produce high fidelity reconstructions.
Thank you. Fascinating. And you've managed to perfectly reconstruct user inputs from model updates. Is that correct?
Yes, exactly. So our method actually does not suffer from this drawback, because in contrast to the prior work, we rather, instead of doing a reconstruction, we extract the data directly from the gradients. And this extraction, first of all, is much more computationally efficient. And it has the advantage that it is high fidelity, in the sense that it extracts the data perfectly, which means without any error, even if the data comes from the same class or the gradients are calculated over large mini batches of data, and even when the data is very high dimensional. So this is all the benefits that we get from our actual data extraction.
And how does that particular attack compare to other attacks that have been proposed in the community?
So as I said already, like most attacks beforehand were really focused on doing some reconstruction. So like changing something into becoming the original data. Yeah. But we observed for the first time that this is actually not necessary, because even for large mini batches of data, when we calculate the gradients over a fully connected model layer, we can extract individual data points from the gradients, because the individual data points are just inside the gradients. They are scaled by a factor. And this factor just depends on the gradients of the bias. And the gradients of the bias is something that is shared from the users to the server, along with the gradients of the weights, such that the server basically, in the end, just needs to take the gradients, rescale them by the inverse of this factor according to the bias, and then it ends up with these data points. So we don't need to do any optimization. We don't need to do any attempts for reconstruction. And we basically just take what is given for free. But probably what's most interesting in this is the question, why is this data directly extractable? And prior work had already shown that when we have a fully connected model layer and we just input one input data point through this layer, this data point is directly extractable from the gradients. And in short, like to give a brief intuition why this is the case, this is basically just when we use the ReLU activation function. Like if you remember the ReLU activation function, it's basically a function which for negative inputs is 0, and for positive inputs is like a linear function. And hence we have this linearity of the input multiplied with the weights plus the bias, and then basically this linearity is invertible. However, why does that also work for larger batch sizes? I mean, then we have the gradients of all individual data points of this batch, and these gradients are just overlaid. And if something is overlaid, we expect that if we reconstruct that, we will just end up with some average or overlay of all data points where we cannot see individual data points clearly. And here is where one of our key contributions in the work lay, is that the observation we made is that even in such cases where we have many more than just one data point, we're able to extract individual data points. And the question is, why does that happen? And it's again the ReLU function helping us, because you can imagine like this ReLU function for negative inputs, it's all 0. And when the input concerning one data point to the activation function is 0, is negative, then the output is 0. And with a 0 output, no information on that data point is propagated through the machine learning model. And when no information is propagated, of course, the gradients at this place will be 0 because there's nothing that we have as information to update on. And if this happens for all data points in the data mini batch, but one data point, so we have all 0 gradients for all but one data point and the gradients for one data point. And even if we overlay them or average them or whatever, then like this overlay will still be the perfect individual data point. And thereby, basically, the case of having large mini batches reduces just to the case where we have a one data point mini batch, where it has been mathematically shown that extraction is perfectly possible. And maybe as a side note, this does not only hold for the ReLU function, but also for other activation functions where basically gradients of 0 can be produced. If you, for example, think about the tanh or the sigmoid, they have these large regions where the function is just super flat. And like in these super flat regions, we can also achieve 0 gradients. And then we have the same case again.
I guess that is a feature of activation functions in general to be able to do that. So you describe 2 threat models in your paper. So there's the honest but curious model, and then there's the malicious model. Can you explain what these 2 are and how they affect the way we understand the vulnerability of a central party?
Sure. Exactly, like you said, we considered 2 threat models for the central party in federated learning, and we can think of the honest but curious central party as a form of passive attacker who does not really deviate from the original federated learning protocol, but it just works kind of with what is given naturally to them. So this honest but curious central party tries to disclose the privacy of the users by just, for example, looking at the gradients that it receives. And for our attack, we show that even such a passive attacker can really benefit from the concept of this leakage that I've just described of the individual data points, because it just receives the gradients and it can basically take out some data points from there from free. And just to give you a little idea on how much data are we talking about, even if we average or let the users calculate their gradients on rather large mini batches with 100 samples on very complex data sets such as ImageNet, such a passive attacker who absolutely and honestly follows the protocol but is just curious, they can still extract over 20 individual data points. So 20% of the data is practically given for free. And then we turn to a second scenario, which is the scenario of a malicious server. And the malicious server is basically someone who can deviate from the original federated learning protocol and do some actions that they are not supposed to do. More concretely, we looked at a case of an occasionally Byzantine server. So that means that the server just often behaves correctly and follows the protocol. But in some cases, like very in few cases, it manipulates something in order to extract even more data. And we thought that this scenario of this occasionally Byzantine server is quite realistic in federated learning, because federated learning, the central parties are often some large companies, and of course they have some reputation to lose, so they wouldn't really want to be malicious all the time and be discovered. That would be terrible. Instead, like, they might just step in some moments where they're less observed somehow. Or we can even think of that it's not a company as a whole, but just some malicious employees, like a group of 2-3 employees. That's usually in large companies all it takes to get a code commit through. They collaborate and then alter this model maliciously, and then basically can, for a very short time, just deviate from the protocol how it's supposed to be. And in our attack, what we exploit this power for is basically to adversarially initialize the weights of the shared model. And we are the first one to consider an active attacker to do exactly this. And previous attacks who have looked in malicious servers have usually looked into how can we exploit, or how can these malicious servers, how can they control some clients to get the behavior that they want to. But we are controlling the weights, and by controlling the weights, we make this data extraction more efficient. So we change, like usually the weights in a neural network are initialized with a random function, for example, a Gaussian or the He or whatever initialization function. And what we do now is to just also do this random initialization, but we make the negative components of the weight vectors slightly higher than the positive ones. And thereby the impact of this negative weights basically dominates, and we create this case where we have the multiplication of the weights and the input data to be negative just much more often than it would regularly happen. And when that happens really often, we increase our chances that it is basically the case that in a mini batch, only one data point multiplied with the weight gets a positive input to the ReLU and gets promoted and thereby can be extracted perfectly.
That is very neat. I'm sure the audience is going to have quite a few questions over that. So happy to break now for questions for a little bit. I do have other questions following, but if anybody wants further explanation on this, because it's pretty important for the rest of the conversation, please feel free to ask. We have, in this paper, you talk about making trap weights to understand differential impact on clients. Can this be considered to be similar to data poisoning? Instead of poisoning data, we poison the model? Another follow-up question. Okay, so then they have a follow-up question. So let's go.
Okay, that's a great question. Yes, indeed. It can be seen as some form of poisoning, definitely. And usually what you want to do if you poison data points is that you want to bring an undesired behavior into the machine learning model. And we just like take the direct path instead of changing some data, which then changes the model. We directly change the model. So it's exactly a form of poisoning.
Okay. And do you think secure MPC frameworks can help mitigate a few of these issues? We can have robustness checks to ensure no trap weights can be used, etc.
I think, yeah, we would be getting to that anyways, probably. There are some ways how people have tried to mitigate attacks in federated learning. One way, for example, is the secure aggregation, which is basically trying to have, instead of sending having each client send their gradients directly to the server where the server can extract them, to have the clients work together to aggregate their gradients together and then only share this aggregate with the server. And in theory, that sounds like a good idea for protection, because then, like, first of all, you have more data which is stuck together. And with more data, individual extraction becomes less likely. And second of all, even if the server is able to extract some of the data, it doesn't know which client this data belongs to anymore. However, that only works in the case of honest but curious servers, because what you can imagine now is that the server basically has this ability, which has been largely studied in literature before, that it can control some fractions of the devices that participate in the federated learning training. And as I said, like per round, we don't have all millions of clients participate, but we just have a few hundred, a few thousand. And it's very likely that a large company has the power to maliciously control these clients, such that they, for example, all only contribute 0 gradients to the secure aggregation, and then like everything is securely aggregated with one target client and all other controlled clients. And then even these aggregated gradients will still, of course, only contain the information on the target client, and its privacy can still be broken. Like a recent work has even shown a more subtle way of doing so, which is basically sending out different models by the server to different clients. So all non-target clients would receive a model where they produce just 0 gradients, and a target client would just receive, for example, a normal model, or we could combine that with our attack and would get our trap weighted model. And then again, like an aggregation, all these 0 gradients would be aggregated with these target clients gradients, and the gradients would still only in an aggregate even contain only information of this particular client.
And with that, you also answered the other question. So I'll get back to the central questions. In the paper, you had said that, and I quote, "For complex image data sets such as ImageNet, the attack yields perfect reconstruction of more than 50% of the training data points. Even for large training data, mini batches that contain as many as 100 data points. For textual tasks such as IMDb sentiment analysis, it perfectly extracts more than 65% of the data points for mini batches with 100 data points. Can you tell us more about the different types of experiments that you ran?"
Sure. So yeah, as you said, we looked into some image data sets like the classic MNIST, C410 and ImageNet, and in a text data set on the Internet Movie Database for sentiment classification. And we basically had two branches of experiments. One was for the passive extraction and the other for the active extraction. And in the passive extraction, what we basically did was we took a fully connected neural network and we looked how different parameters influence this extractability of individual data points that I've been talking about. And we looked basically into two main parameters that have an impact on the success. The first one is the number of neurons that we have in this first fully connected layer where we do our extraction. And the second one is the batch size, like the mini batch size at the clients. And we can think of if we have more neurons, then basically we have more gradients, and each pair of gradients basically gives us a chance for individual extraction. So it's just like having more potential chances. And of course, with like the batch size, if we have smaller data, then we observe that there will be probably less data that can overlay. And indeed, what we found in our experiments was that the more neurons we have, and of course, the smaller the batch sizes that the clients are, the better extraction gets. So with small enough batch sizes or large enough number of neurons, we are even able to extract all data points that the clients have trained on. And we've even looked at the fact, is it necessary that we really reinitialize this model every epoch again for performing this passive attack? And it turns out that no, because even over training, even when the model improves in accuracy, still relatively constant amounts of data points are individually extractable. So this is great news for the server that wants to learn about private data of the users, less great news for the users who want to protect their privacy. And for our active attack, we basically looked at the same experiments, but we played also with different initializations for our trap weights. So we looked into how to make the trap weights such that they can even exploit or extract more data points, and we looked into how to make them unnoticeable, such that like clients would not be suspicious, but rather the weights would just look like normal model weights, and it would be impossible for clients to tell apart whether the model they have received is a maliciously initialized one or just the result of previous training processes.
Fascinating experiments. What are some of the most surprising discoveries that you've made doing this research?
Well, I guess the most surprising one for us was that all you need to break privacy in federated learning in this setup basically is matplotlib, because we just showed that the gradients of even these large batches contain individual training data points. So if we just take the gradients, rescale them and plot them, we will see individual data points. And like when I first ran this experiment, I was completely stunned to see some of my individual data points back, because I had really just expected this average. But of course, it was also really surprising for us to see how powerful weight initialization of a model can be. Previously, such weight initializations have been heavily studied to look into model convergence, like how can we train the model faster, more efficiently, etc. But we have now also shown that this weight initialization might have an impact on the privacy. And I think this is a very surprising and also very promising future direction.
It is very surprising. I'm really looking forward to seeing what other research comes out of it, to what weight initialization can, how it can help with privacy instead of making it worse. What is the role of, what would you say is the role of differential privacy in federated learning now that you've done this research?
So basically, federated learning in its standard form does not give any privacy guarantees, right? It's not per se a privacy technology. It just is supposed to offer some form of confidentiality, because this raw data never leaves the device. And basically through our attack, we saw that this is not the case, but leave that alone. But differential privacy is really a technique which is supposed to give us some privacy guarantees that basically bound the privacy leakage of specific sensitive user information. And there are different ways how to implement differential privacy into the federated learning protocol. The first one is like the standard differential private federate averaging, which is like a differential private way of performing distributed stochastic gradient descents. And the clients basically take their gradients, clip them, and send them to the server. The server applies the noise and then does the model aggregate. And of course, you can imagine that this is not a suitable application when the server is malicious, because the server might just not add the noise, or the server might extract the data from the gradients and then add the noise. So there's basically no protection in this scenario. And then there is local differential privacy, where users locally add enough noise to protect their own data. Like, this is like still always an open question, what is enough noise? But let's say they manage to add enough noise and then share the gradients with the server. This is potentially a case where the privacy can be completely protected. However, it has been shown that local differential privacy has a terrible privacy utility trade-off, because the amounts of noise that are added are just too large. And as a form of mix between the two, distributed differential privacy has been introduced, where the clients locally add some amount of noise. And then in the form of secure aggregation, for example, by putting together all these slightly noisy gradients, the amount of noise will be enough to protect the joint gradients and yield high enough privacy guarantees. But of course, we have seen already, I've told you that there is a problem with the secure aggregation also in the malicious server, because even here we could think of the server manipulating some of the clients to always send these zero gradients. And the other clients, if they don't have a way to verify that, it will be exactly the case again that the gradients of one client are aggregated with these all zero gradients. And if in that case, the local amount of noise of this client was not sufficient to protect the client alone, we will still end up with not high enough privacy guarantees.
So what would it take to make federated learning robust against a malicious adversary then?
We thought about this question for quite some time, and for us it seems somehow difficult, even if the server acts maliciously only in a very few cases. There are some things, of course, that we can prevent. For example, this fact that the server sends out different models. This can be prevented, for example, if the model is locked in some kind of blockchain, which is centrally accessible by anyone, and the clients can verify whether they obtained the right model or not. It is also possible probably to prevent our active adversarial reinitialization. So we could think of a scenario in which the server initializes the model in a trusted execution environment and all the updates are performed there. So at least in this case, it will not be possible for the server to put some wrong initialization or to reinitialize in the meantime. Still, there's this problem that this does not prevent a passive leakage, and we've shown that even in this passive case, 20% of the data can be extracted, which is of course too much to say that it's privacy preserving. And the question is also on the control of other clients. So if the server even controls a small fraction of clients, it still can do the attacks like it described. And it's very difficult for clients to verify that other clients are not corrupt, because they, first of all, don't have direct communication channels usually. And even if they had, like, what would it take for someone to prove to someone else that they are not malicious or that they are not controlled? So this is an open question and a problem in making it private. And with differential privacy, we've also seen that it only works if the clients add enough local noise, which then again comes at the cost of utility or accuracy of the model. And what we took out as a baseline message for us was at least that clients should just not participate in federated learning protocols when the server is not trusted. And if you're a trusted party and you want to employ federated learning in a private way, basically what is the minimum requirement? Would it be to have the clients add enough noise locally, perform some form of secure aggregation, have the clients compute their gradients over large batches normally, version the model and upload it to a point where it can basically be verified by the client, and perform your updates in a trusted execution environment.
Awesome. Thank you, Franziska. That is very insightful. We're opening the floor for questions now. If anybody has anything else to ask in the Q&A or in the chat, feel free to do so. Right. Stunned silence. It seems like you got questioned out for those two questions in the middle. All right, just leaving it 5 more seconds if anybody has anything to ask.
Because I can also offer that if anyone doesn't dare to ask questions right now, they can just contact us on social media afterwards, and we'll get in contact.
Yes, absolutely. Any reaction from folks at Google after your paper came out?
We did not have any direct interactions with folks from Google.
Okay. Lots of thank yous. All right. Well, Franziska, thank you very much. Would you like to drop your social media information in the chat or your email for people to ask you more questions?
Yes, that sounds like a good idea. Let me do that.
Thank you. So normally you're in Berlin, but currently you're in Toronto. So
exactly. Unfortunately, turning back next week, but hopefully coming back. So I posted the link to my LinkedIn profile in the chat. So feel free to reach out and discuss.
All right. Thank you very much, Franziska. Always so
Thanks
much fun to speak with you.
Same for me.
Have a great day. And thanks everyone for attending. Really appreciate it.
Bye.